hello to everybody. And I'm very pleased to have here Mohammad Farhat, and that will be a kind of first time we present some result of our group in this AstroGeo Seminar. So Mohammad has just defended his PhD thesis. It was on the 5th of January, in fact. And he has spent 3 years in our group. He's from Lebanon. He was at the American University of Beirut for his master thesis with Jihad Touma. And then he came here, and he was right in time for the COVID. So it was a kind of difficult start, but I think we managed to cope with that. It was not very easy for him at the beginning, but then I think everything went fine. And so he will speak of the latest results on the tidal evolution of the Earth-Moon system. So Mohammad, you are welcome now to share your screen, and we can hear you.
So as Jack was saying, I'll present a part of my PhD work within the AstroGeo team at IMCCE, our lab, work that I have done with Pierre-Claire de Retour, Gwenaël Bouet, under the supervision of Jacques, basically on the tidal evolution of the Earth-Moon system over extended geological timescales. And it basically, so this work basically extends a rather long thread of a pretty rich narrative that explores the dynamical evolution of the Earth-Moon system over various time scales between the formation time of the system and the present. So to start with, just to put things in context, basically, as far as we know, the Earth-Moon DO is not a very common planet-satellite DO, at least in the solar system. So setting aside the system of Pluto and Charon, the satellite-to-planet radius or mass ratio in the Earth-Moon system is the largest among all known analogs, in fact, of the solar system, including Martian Phobos and Deimos, Uranian satellites, Saturnian and Jovian satellites. And this property is very critical. In fact, it is a very critical characteristic of the system when it comes to tides, which are the focus of our talk today, and how much tide would basically contribute to the long-term evolution of the system. So this large satellite to host mass ratio in the Earth-Moon system would tells us that tides would dictate or basically control the long-term evolution of the system. Moreover, for the moon specifically, the precise interior structure of the moon is yet to be defined, but with more advances in more recent years, it's becoming clearer with time that the moon has a tiny sized core of ambiguous nature. We still don't know if the lunar core is differentiated or not. That is enveloped by a mantle, which is similar to the mantle of the Earth. But more importantly, in the early stages, there was also an envelope of a molten magma ocean, or at least partially molten magma ocean, in the very early hot stages of the moon. And these features, along with many other features, especially having to do with the large angular momentum present in the system, they would require an intricate model of the formation and evolution of the Earth-Moon system to be satisfactorily explained. And although we have extensive theoretical modeling and observational measurements on the system, the Earth-Moon system still presents some outstanding or perhaps perplexing problems that we need to address. So on the formation side, it was not until the 1980s, in fact, that the lunar genesis via the giant impact scenario has emerged as the leading hypothesis, as it seemed best capable to explain these features that I've just described. So the small lunar core, the early hot start of the moon, and it was also able to account for the large angular momentum in the system. So in the most probable scenario of this hypothesis, we have an impactor, which is the size of Mars, colliding with a very high momentum with a very fastly spinning Earth, and leaving behind a proto-moon with a disk of ejecta in which the moon can co-accrete into the moon that we know of today. And so this scenario explains, as I'm saying, various features, but it leaves us with more problems that we need to think of and that are still basically presenting some conundrums or unsolved problems that need to be addressed. And I'll discuss a few of these before jumping to the focus of our work here. So first, the so-called isotopic crisis, which basically entails that if the moon has formed primarily from this, if the moon formed by this giant impact scenario, it should primarily form from the material of the impactor. And so we expect a lunar chemical composition, which is similar to this external impactor. But this is not the case, as it turns out, because the Earth and the moon have very similar chemical composition over a range of isotopes that trace the origin of planetary materials, as shown here, for example, for 3 stable isotopic ratios that are due to nucleosynthesis anomalies. So the Earth is anchored to 0 by definition, and the moon is the red square that you can see. And you can see the overlap between the vertical lines and the lunar composition, indicating that the Earth and the moon are basically almost compositionally identical twins. So the likely resolution of this problem has to do with the momentum of the impact scenario. So a higher momentum would leave a disk of ejecta that has more mixed composition, thus solving this problem that we have, and which is called the isotopic crisis. Another problem of reconciling the aftermath of the impact with present observables is the so-called inclination problem. And so this problem basically entails that if we look at the moon today, we know that the lunar orbit does not live exactly in the ecliptic, but it has almost a 5 degrees offset from the ecliptic. And if we trace the evolution of this lunar orbital inclination backwards in time, so at present the moon is at 60 Earth radii, it has this 5% inclination. And if we try to trace the evolution with classic tidal models backwards in time, we find that the moon had a high inclination, almost to 12 degrees from the Earth's equator when it was very close to the Earth upon formation, which is inconsistent with what we expect from this giant impact scenario, because the disk should co-accrete in the equatorial plane of the Earth and not off this equatorial plane. And the likely resolution of this problem is through certain dynamical processes that happen early on when the moon was very close to the Earth. So we do start with a moon which is in the equatorial plane of the Earth, but some dynamical resonances occur, exciting the lunar orbital eccentricity and inclination, so that we end up with this 12 degrees or so, and so we continue the evolution until the present. But the problem that we focused on in our work, and I'm going to focus on in this talk, is what's called the timescale problem of lunar origin. And it's another reconciliation problem with the aftermath of the impact with current observables. So this problem basically corresponds to the inconsistency between long-term tidal modeling of the geologically between long-term tidal modeling of the Earth-Moon distance and the geologically constrained age of the moon. So here I'm plotting the Earth-Moon distance in Earth radii. So the moon at present is roughly around 60 Earth radii, moving backwards in time in giga years, in billions of years. And so tidal modeling basically have a variety of models that are based on different assumptions on how the Earth would react to the tidal forces of the moon and the sun. But mainly over the past century, they have been pertaining to bodily tides, such as the constant time lag model or the equal phase lag tidal model. And without expanding on these models mathematically, it turns out, because they have been extensively used over the past century, and it turns out that whatever model we use, if we start by the present rate of recession of the moon, the present rate at which the moon is receding away from us, and we use these tidal models, we end up with a lunar orbit that collapses onto the Earth between 1 and 2 billion years ago, which is in clear disagreement with the age of the moon that we know of and that we constrained from geological data that we collected from the surface of the moon with through the series of Apollo missions, which is roughly the age of the Earth, 4.5 billion years. So The disagreement also extends to a disagreement with geological data. So we have a bunch of geological proxies that would tell us or that would probe the history of the Earth-Moon system and would tell us the whereabouts of the system over time. So we have cyclostratigraphic data, we have tidal rhythmites, and I do not have really much time to go over this data, but I advise you to go to the recent talk of the AstroGeo series by Linda Hennov's last talk, which is Linda Hennov's last talk, who really gave a very nice overview of the history and the state of the art of these geological inferences of astronomical quantities. So the problem, so this inconsistency between tidal modeling and the age of the moon is what we focused on, which is called the timescale problem of the lunar origin. And it basically comes down to the following. So over the past decades, basically, we realized that these simplified tidal models that I just described, they cannot really characterize the tidal response of the Earth because they are effective models that consider the Earth as a homogeneous layer, where in fact the Earth is far from a homogeneous layer. We have a solid mantle, a core, and we have the oceanic layer, and these layers respond drastically differently to the tidal forces of the Earth and the Moon. So we cannot consider the Earth as a homogeneous layer that responds with a single response to tidal forces. So we have the solid Earth, which deforms in response to these tidal forces in a certain manner, in a certain spectrum, and this response is delayed due to the viscous nature of the mantle. And we have the fluid layer, which also responds to the tidal forces of the Moon and the Earth. And the response is also delayed due to some dissipative mechanisms that happen in the ocean. But these delays are not the same. In fact, we have offset of these delays. And it was not until the late 90s, in fact, after the Topex-Poseidon satellite measurements, that we were able to basically entangle or separate the contributions of both the solid and the ocean on tidal perturbations using altimetric measurements. So from perturbations on geodetic satellites, we have the contribution of both components, and from altimetric measurements, we have sensitivity only to oceanic components. So we were able to separate these contributions of tidal dissipation, and plotted here is the amplitude and the phase of the semi-diurnal tide, and you can see the clear separation between the solid and the oceanic tidal dissipation. And also here we have properly modeled the effect of each component on the present variation in the length of day on Earth. So the solid component would contribute to roughly a minor contribution of roughly 6%, and the ocean with an anomalous high dissipation at present, which we describe as a resonant dissipation state, it contributes roughly 94% to the present variation in the length of day of Earth. So the key point is that to address this timescale problem of the lunar origin, it was realized over the past half a century, if you want, that oceanic tides have to be properly modeled, not an effective model of the Earth, but proper modeling of oceanic tides. And the question at premise is that how to model the oceanic response such that at the present we have this anomalously high dissipation, but it was varying in the past so that we do not have this early collision between the Earth and the Moon. So before dissecting our model in details, I just want to put it in context of the literature and its state of the art, just to make more clearer our contribution to this problem. So we have maybe a handful of seminal works that used oceanic tidal modeling to study the evolution of the Earth-Moon system. And these works can be basically classified into two approaches. So we have a semi-analytic approach that addresses oceanic tides from a semi-analytic perspective. And this basically uses effective models of simplified geometries of the ocean and the continent. And it basically relies or assumes that what would place the present ocean into a resonant state of anomalous dissipation is the rotational velocity of the Earth, because the rotational velocity of the Earth or the length of day of the Earth is what regulates this tidal dissipation in the oceans. So noteworthy of these works is the work of Webb, 1982, who considered a hemispherical ocean, an equatorial ocean, and a hemispherical supercontinent. And he had two free parameters to describe oceanic dynamics. So he prescribed these two free parameters and ended up with this evolution of the Earth-Moon distance. So in all the figures that I'm showing, you have a plot of the Earth-Moon distance backwards in time. So similar also to the work of Webb was the work of Hansen in the same year. So he had also a hemispherical ocean, because this simplified geometry could be dealt with analytically. So he also had a hemispherical ocean, but he studied two configurations, an equatorial ocean or a polar ocean. And more recently, we have the work of Tyler, 2021, who absorbed, so he did not consider any continent or any continental effects, but absorbed the effect of continentality into free parameters of the oceanic model. So he considered a global ocean, no continents, and absorbed the effect of continents into a free parameter of dissipation within the oceans. And he tried to constrain this free parameter to have an evolution curve of the Earth-Moon history that fits a bunch of geological data. In parallel and in contrast, we have a completely different approach, which is basically completely numerical, and it does not deal with simplified geometries, but rather with exact or precise continental distributions. So you get a continental paleogeographic reconstruction, you input it into a code, and you compute dissipation. And notable here is the work of Green et al. 2017, who had 6 paleogeographic reconstructions over the past 250 million years and computed dissipation for each of them, oceanic dissipation, and then interpolated between these dissipations to have a history of the Earth-Moon distance over the past 250 million years. And then we have more recently the work of Daher et al. 2021, who considered 4 of these paleogeographies and then assumed that each one of them is fixed in time to create these 4 evolution curves of the Earth-Moon distance, and then sampled using MCMC between these geometries to have this ensemble in gray of possible evolution curves. So although every one of these works have really made us understand something about oceanic dynamics, what stands out is common to all these works is that we do avoid the early collision between the Earth and Moon between 1 and 2 billion years ago when we account for oceanic tidal dynamics, but we are left with a lunar orbit that is considered a high orbit at the time of formation of the Moon. So the Moon should form, as we said, very close to the Earth at few Earth radii, but what we see here is that the Moon at the time of its formation would still be around 45 Earth radii here, around 30 Earth radii here, 50 Earth radii here. So we still have an inconsistency between what we expect from formation and the evolution history that we have from these models. More importantly, we cannot really rely on paleogeographic reconstructions to compute tidal dynamics for one simple reason. First, at present, we do not have a continuous model of plate tectonics and continental drift over the whole history of the Earth. But more importantly, it looks very hard to have a precise model of continental evolution. In fact, it is estimated that the world uncertainty, which is the percentage of the lithosphere that has already subducted at a certain point in time, and it's thus unavailable for plate tectonic reconstructions, grows by as much as 60% by 200 or 220 million years ago. So we cannot really have precision in this modeling. And if it is the effect of continentality that controls the evolution of the Earth, then we cannot say much about this history. So this left us with a question to address at the beginning of addressing the problem, which is, can we really construct a model of the Earth-Moon history using oceanic dynamics, of course, that fits first the present rate of lunar recession, because this is measured using lunar laser ranging to millimeter precision. We know how much the Moon is moving away from us, and this is a direct observable that we need to respect. Another direct observable is, or constrained data point, is the age of the Moon, which is geologically constrained. So we need to respect these 2 data points and constrain any evolution model by these 2 data points. And we want to avoid an imposed fit to geological data for reasons that I will make clear later, but basically because some of the geological data are dependent on tidal models. And so to avoid any kind of circular reasoning, we want to avoid this kind of fit. And we want to avoid the complete dependence on continentality because of this uncertainty growing backwards in time. So this was our motivation in addressing the problem into creating our model. So to describe our model, we basically had to include several elements to allow for as much physical insight as we can into our model. So to start with, we had to decide, because we work with the semi-analytical approach, so we had to decide on a simplified oceanic geometry. So we will not work with the numerical approach. And we had to decide on what kind of geometry to use for the ocean. So we have two simplified geometries to use: a global ocean and a hemispherical ocean with a hemispherical continental cap. So from a lot of evidence that we have collected, so we have analysis of the detrital zircon around 4.4 billion years ago, 4 billion years ago, on the interaction between an early ocean and the continental crust, and from isotopic studies of oxygen, hydrogen, other isotopic ratios, all indicating the existence, at least, of an early Archean ocean on the surface of the Earth. Moreover, we have, in recent studies, experimental evidence, not only on the existence of such an ocean, but on the voluminous nature of such an ocean. So in a study of, in the study of Dong et al. 2021, the author established a temperature-dependent water storage capacity model for the Earth's mantle. So basically, we have an exchange of water between the reservoirs in the mantle and on the surface. And their experiments depicted that the early mantle, which is significantly hotter than the present, was characterized by a water storage capacity. So how much would the mantle hold of water? That is much lower than the present. And so due to this continuous exchange, estimates of water content in the mantle being greater at present than its storage capacity in the early Archean means that the early Archean oceans must have been voluminous and could be even larger, as the authors inferred, than at present. So in our models, we allow for an early Archean global ocean. So we have a global oceanic, a spherical oceanic shell of uniform thickness. So the uniform thickness of this ocean is the first free parameter of our model. And we try to compute the tidal displacement of this oceanic shell, allowing also for the effect of the solid, which is often ignored in the literature in oceanic tidal modeling. So we have the mantle, which is also deforming, and we use an Andrade rheology to model the deformation of this mantle. And so we not only we have the surface displacement of the oceanic surface, or the tidal displacement of the oceanic surface, but also the deformation of the solid surface. And what matters eventually is the difference between these two surfaces. So we allow for coupling effects between the solid and the ocean. So we allow for the loading effect of the oceanic shell on the solid. We allow for the effect of gravitation and self-attraction between the two, and for dissipation inside the mantle itself, which will prove to be of a critical significance, especially in the earliest eons of the Earth-Moon system. So we have a global Archean ocean with a free parameter, which is the uniform thickness that we need to decide on. And moving forward in time into the Precambrian, into more recent eons, from zircon crystallization analysis and paleomagnetic data, we have models of crustal volume evolution and growth of the crustal volume. So here I've just collected a sample of these models from the literature, which can be basically representative of the evolution curves that we see in the literature, all anchored at the present to the volume that we know of for the crust, which is 100%. So these curves are based on the presently preserved proportion of rocks with either different geological or crust formation ages. And these models, although they look irreconcilable, but for us using simplified geometries, they at least agree on two limits. So we have the limit of a global oceanic coverage in the earliest eons, and the present, which can be modeled by a hemispherical ocean. And this is the kind of modeling that we use in our model. So we allow for a transition into a hemispherical ocean in the more recent eons. So we allow for a hemispherical oceanic shell with a hemispherical supercontinent, which imposes boundary conditions on the tidal flow in the hemispherical oceanic shell. We also allow for the solid here for the coupling between the solid and oceanic layer, and so the same. We have the oceanic thickness free parameter. So the first free parameter, as I said, was the uniform oceanic thickness. The second free parameter is a time scale or a frequency, inversely, of the dissipation that occurs in the oceans. So pathways to dissipation in the oceans are yet to be established precisely quantitatively, but the general picture has become clearer in recent years, and it is established that the large barotropic tidal flow, which is of large wavelengths in the ocean, loses most of its energy to bottom friction when interacting with the surface topography in shallow seas, but also for a significant part, it loses energy over ridges in the open oceans, and another unconstrained part happens over continental shelves and continental slopes. So barotropic tidal currents, which are predominantly horizontal, of large wavelength, large structure, would interact with these vertical structures of topographical patterns, and would generate vertically propagating waves that would allow for oscillatory waves or internal waves that would dissipate energy much faster because they are of shorter wavelengths. So different mechanisms of energy dissipation happen in the ocean, and they are not really quantified precisely, but we model that by a time scale of depletion of energy from the oceans, or inversely a frequency of this depletion of energy from the ocean, which we call sigma r, or a Rayleigh drag frequency. So another element that we take into account is that, so we have a hemispherical continental cap in the recent eons, but we need to decide on the position of this hemisphere on the surface of the Earth, because it turns out in our study that where we place the hemispherical ocean would affect the tidal response of the Earth. And so what we did was that we coupled that with plate tectonic reconstructions. So we used a model of Meredith et al. 2021, which is, to my understanding, the first continuous model, kinematically continuous model of plate tectonics over the past 1 billion years. And so because we're dealing with a hemispherical continent and not with precise geometries, we compute the center of mass, or the geographic center of this continental distribution, and we place the center of our continental cap at the center, at this geographical center, which evolves with time. So here I'm plotting the latitude of this evolution of geographical center over 1 billion years, and it basically moves from and so our hemispherical continental cap is basically equatorial now, almost, and we move into the Mesozoic with almost a polar ocean, polar continental cap, and then we go back into more earlier times, back into an equatorial ocean, where we trace this evolution of the surface geographic center. So we have an early Archean global ocean. We transition into a hemispherical ocean that is coupled to plate tectonic modeling. We have two free parameters, the oceanic thickness and the time scale of dissipation in the oceans. And now we need to compute oceanic dynamics. So now is the mathematical part. And I'll just touch very tangentially on this, just to give you a sense of what we're actually computing here. To compute tidal dynamics, basically, we solve a system, the governing system of equations, which is a system of momentum and mass conservation inside the ocean. So a classical Navier-Stokes equation reduced to allow for analytical handling. And so we have the derivative of the velocity, the dissipation time scale, or the frequency that I described. We have the Coriolis term, which brings the effect of rotation of Earth into tidal dynamics, and we have the tidal displacement and the equilibrium tidal amplitude. The mass conservation equation, we have the derivative of this displacement, the horizontal flow, which gives the oceanic thickness, and we basically attempt to solve this system in the shallow water approximation. So we consider only the large-scale barotropic flows, not the baroclinic component, over bounded domains on the sphere, so either a global or a hemispherical ocean. The tidal flow would be, in our methodology, a superposition of modes, each with its eigenfrequency, with a direct dependence on the tidal frequency sigma. So we solve the system spectrally at each tidal frequency sigma, and the tidal response computation is strictly dependent on which geometry we use for the oceans. So just a brief recipe on how we compute tidal dynamics for these geometries. So we take the system, for example, for the global ocean scenario, and we decompose or we expand all our quantities in Fourier components, because we consider the linear approximation, which tells us that there is the response of each given mode in the oceans is directly proportional to the corresponding component from the tidal forcing perturber. So we expand these equations in Fourier series, and then we expand the Fourier components into a set of horizontal functions, the latitudinal complex Hoff functions, which are functions that describe this large structure of oceanic dynamics on the sphere. And they only vary latitudinally, and they are complex functions, and we interpret them as Legendre polynomials that are distorted by the effect of rotation. And so with that, we recover the horizontal flow of tides, which is described by the Laplace tidal equation, which is an eigenvalue eigenfunction equation, with the Hoff functions that I just described serving as the eigenfunctions for of this equation. And then once we construct this horizontal flow, we solve for the vertical structure of tidal dynamics to solving basically for the tidal displacement of the ocean, which couples the ocean to the solid surface. And so our tidal displacement is an expansion of displacement components, with the coefficients being change of basis coefficients between Legendre polynomials and Hoff functions. And to solve for this tidal displacement, we basically need to solve a linear system that includes the tidal forcing functions and characteristic frequencies that couple the horizontal flow to the vertical flow. So once the solution of this algebraic system is established, we have the complex love number, which self-consistently describes the tidal response of the Earth. So we have this love number, and we intentionally avoid to use the classically used quality factor of the Earth for reasons that we describe, that we can discuss further if you want. But this complex love number, which describes the response of the Earth, basically allows for the solid dissipation in the solid part of the Earth. So this is the love number, tidal love number in the solid, the loading love number in the solid, which couples the oceanic shell with the solid shell, and tidal displacements happening in the ocean. So it's a self-consistent function describing the whole response of the solid and the ocean together. And it's basically the most important quantity for us, because it is directly proportional to the tidal torque. And the tidal torque is the rate of exchange of angular momentum between the Earth and the Moon. So it's the rate at which the Moon is moving away from us, and the rate at which the Earth is slowing down its rotational motion. So this is the quantity which basically we are after. So it's directly proportional to the imaginary part of this complex love number. So basically, to compute the evolution of the Earth-Moon system, we have to compute the amplitude and phase of this complex function. So similarly, for the hemispherical ocean, things get a lot more complicated, and I will not go into the details of that. But because we have the hemispherical continental cap, it basically imposes boundary conditions that would change the formalism by which we solve for oceanic dynamics. So we have to expand the horizontal flow into a divergence-free and a curly-free components. And this is the basic assumption. And then we impose the condition of impermeability on the coastlines of the continental cap. So it basically changes the whole formalism of how we compute tidal dynamics, even though we're just using a simplified geometry for the ocean, but it still imposes a lot of mathematical complexity when we have to solve for oceanic dynamics. So as I said, the important quantity to compute the evolution of the Earth-Moon system is this torque, which is the rate at which the moon is moving away from us and the rate at which the Earth is slowing down its rotation. And so I'm plotting here spectra of this torque. So the torque, the logarithm of the torque as a function of the frequency or a normalized frequency, which evolves in time. And you can think of it by imagining that as we move backwards in time, we are moving along the positive direction of this frequency. So as we said, we have two free parameters for our model. So one of them is the dissipation frequency, sigma r. So each panel corresponds to a different value of sigma r. And we fix for all the 4 panels an oceanic thickness of 4 kilometers, which is similar to the average thickness of the Pacific Ocean. And we're plotting the torque, which results from the global ocean and from the hemispherical ocean. And you can see that if we allow for a very large value of sigma r, we have a smooth regularity and the smooth variation in the...
Mohammad, maybe it's good to state that omega is roughly the speed, the rotation speed of the Earth, so the length of the day.
Yes, so yeah. So omega is basically a combination of the rotational speed of the Earth and the orbital mean motion of the moon. So it corresponds, it's basically dominated by the variation of length of day in the Earth. So as I said, as we move backwards in time, the length of day is decreasing. So omega here would be moving in this direction. So we start at present with omega approximately equal 1. So this is the value omega at present. And as I was saying, if you allow for smaller values of this dissipation frequency, which we start having these resonances in the tidal torque fleshing out from the tidal spectrum and getting more defined, more amplified as we allow for more and more dissipation timescale. So you see these resonances fleshing out of the spectrum and getting more amplified and more defined. And you can see that the hemispherical ocean have a far less regular spectrum than the global ocean. In the global ocean, the resonances are uniformly separated. We have kind of regularity, but because of the imposed effect of coastlines in the hemispherical continent, we have this irregularity in the spectrum. And so at present, as I said, we live around 1 for the Earth, and moving backwards in time, the rate of change of the Earth's length of the day and the lunar distance would be living along these resonances and surfing them, as we will see in the next few slides. And these resonances will be of critical significance of how to shape the evolution history of the Earth-Moon system. One more key point that I want to focus on is the effect of accounting for solid effects, even though we said that solid dissipation at present is only 6%, but this is not the case all over history, because also when we move backwards in time, as we go into positive omega, you see here I'm plotting a pure oceanic response and then a response coupled oceanic with solid. And you see that as we go backwards in time, the two curves diverge, meaning that the solid contribution would be much more significant, and the effect of it would be much more significant when the Earth was rotating much faster than it is rotating today. So it's very important to take the effect of solid when we model the whole history, even though it's only a minor contribution at the present. So as I said, we have these geometries, we have these free parameters, and so now we need to decide on these free parameters. So we have two free parameters, oceanic thickness, dissipation timescale, and we need to decide on this. And as I said earlier, we only take into account the two most constrained points of the lunar orbital history, which is the rate at which the moon is moving away from us, which is measured using lunar laser ranging to sub-millimeter precision, and the age of the moon, which is also constrained to a good precision. So we take these two constraints, we have two free parameters, sigma r and h, and we have these two constraints, and on a grid of these two free parameters over a range of values, we compute for every pair the corresponding evolution of the Earth-Moon system. And then we see for this evolution, for every pair of these parameters, what age of moon we get and what what rate of lunar recession we get at the present. And so we're constructing here a misfit surface with our two observed constraints. So dark blue regions correspond to the pairs of our free parameters that would give us an evolution history of the Earth-Moon system that properly accounts for the age of the moon and the current rate of lunar recession. And we do so for 3 models, just to compare with the literature. So a global ocean model all across history. So we have these minima of the misfit analysis. A hemispherical ocean to compare with the work of Webb all over the history. But more importantly, our model, which is what we call the combined model, which transitions from a global ocean in the Archean to a hemispherical ocean at the present. And so, first of all, we did find a pair of parameters that would give us an evolution history of the Earth-Moon system that has the proper age of the moon and the proper present recession rate. But more importantly, this pair of parameters is unique, so we do not have a degeneracy in the problem. And even more importantly, this pair of parameters makes sense physically, because we can get a pair of parameters that's like 20 kilometer thickness for the ocean, but we get an oceanic thickness which gives an oceanic volume which is only 10% of the presently measured oceanic volume from global relief models. So this is the oceanic volume we get, and this is what's estimated from global relief models. And we get a dissipation time scale in the ocean that is well within experimentally constrained intervals of dissipation of energy within the oceans. So we do get a pair of parameters that would give us this history, and more importantly, these parameters make sense physically. So where would that leave us with our evolution? So I'm plotting here the Earth-Moon distance going backwards in time. And as I said, we have these geological data which tell us the history of the Earth-Moon system over different times, and they are into different sets of data. So we have the tidal rhythmites. So this is one bunch of them. And we have another set, which is the cyclostratigraphy set of data. And you can see why we cannot really rely on fitting our model to this data, because it's impossible to fit an evolution curve to these data points, because at the same time you can have 3 inferences that have the almost at the same time they have different values of the Earth-Moon distance, and we cannot really fit an evolution curve to these data points. So decided to ignore them at the premise of our model and then compare later. And so this is for a global ocean model, so a global ocean all across the history of the Earth. So we get the proper age of the moon at 4.5 billion years ago. We get the proper rate of recession of the moon, but you see it misses on almost all of the geological data points. And so for the hemispherical ocean, just to compare with the literature, as I said, and here is our combined model. So we have our combined model that transitions from a global ocean to hemispherical ocean. It gives the proper age of the moon at 4.5 billion years ago. It gives the proper rate of recession of the moon at the present. And I think strikingly, it gives also a very good agreement with the cyclostratigraphic data, especially those newer data points that we have, which are Latnik et al. 2022 and Meyers and Malinervo cyclostratigraphic inferences. So we have this evolution history that fits the observables and is in good agreement with the geological data. And it's basically, as I said, shepherded by these resonant excitations in the ocean. So here I'm plotting the resulting tidal torque. So as we said, in more recent eons, we have the hemispherical ocean. In more earliest eons, we have the global ocean. And you see these resonances in the blue curve in the ocean that would give us a variation in the rate of change of the Earth-Moon distance. So 2 small resonances here would give us this cascade of variation, which is, in hindsight, a good fit to the geological data because of the irregularity that you see here in the data. It's not a smooth variation. And then we have the major resonance that occurs in the global ocean that gives us this very significant and relatively abrupt variation in the Earth-Moon distance that we see here. And so between these resonances, we almost have what I call a dormant torque, so not much resonances, so a smooth variation of the Earth-Moon distance that would explain these cyclostratigraphic inferences. And then we have the impact runaway effect, where the moon collapses onto the Earth at its proper formation time. So I think it's very important looking into the future to see more agreement or disagreement between future geological inferences and this modeled curve, especially around resonances, because these are notable features of this model. So they would tell us of significant variations, and it would be nice to see if future cyclostratigraphic or other geological inferences would match these significant variations in the Earth-Moon distance. And so what we also managed to explain with this model is that the present is in fact an anomalous dissipation in the oceans. So at the present, this is the average of the torque, which is proportional to dissipation. And so the present is, and this is logarithmic, of course, so the present is high enough. So it is an anomalous dissipation happening in the oceans. So we do not need an intricate model of continentality to explain how to push the Earth into a resonant state of dissipation, but we captured that with a simplified geometry. And so we have this anomalous high dissipation at present, which is basically much larger than most of the Earth history, except for these resonances. So we also compute the evolution of the Earth's length of day and obliquity, with these resonances also having their significant impact. But more importantly, these could have significant paleoclimatic signatures, because obliquity would basically contribute to the insolation that the Earth would get and the climatic consequences that we have. And the length of the day is also linked in many studies to the evolution of life on Earth. So it would be also nice to see a possible correspondence between this kind of evolution of obliquity and length of day and any paleoclimatic major events. So to summarize, I think I'm on time. We just revisited the outstanding timescale conundrum of the lunar origin, which is the difference between tidal model, the inconsistency between tidal modeling and the proper age of the moon, with recent advances in semi-analytical solid and oceanic tidal modeling, because as we said, we cannot really rely on continental reconstructions. We constructed a model that properly accounts for the measured present rate of lunar recession and the lunar age, and we recovered an evolution history of the system that is in good agreement with geological proxies, although we did not impose this FID a priori. And it remains to further implicate this reconstructed history, as I said, with additional geological proxies and the existence, or perhaps not, of predicted paleoclimatic signatures. So to finalize, I will just want to indicate again that the results of this model are now on the AstroGeo website that you see here. So you can go to this website, and if you go to the AstroGeo data tab, you can find, you can plot this solution. So you have the AstroGeo 22 is what we called it. So the AstroGeo 22 solution, and you can plot the evolution of the semi-major axis, the evolution of the length of day, the evolution of the precession frequency, the axial precession, the tilt precession frequency, and time. And you can have the raw data files of these evolution histories. And you can also, if you have new geological or maybe cyclostratigraphic inferences of these quantities, the team has created a tool to see your data point and add it to the literature around the curve. So it's a tool that's easy to handle, and I think it's best explained by the recent video that's uploaded to the YouTube channel by Jacques, who gave an overview of the website and the tool and how to use it. And with that, I end, and I thank you for listening.
So, thanks a lot, Mohammad. Thanks for this very detailed account of this work. And now we are open for question. Margaret?
Margaret, you still have questions?
Yeah. Hi. Well, thanks again for the presentation. Very nice. Yeah, so I have a couple of questions. So the first one is looking at this huge resonance at 3.2 billion years ago in the tidal torque spectrum. Do
Yep.
you have any idea why it is much larger than the ones in the more recent past? Because in those earlier plots that you showed, where you show the tidal response versus the rotation, Earth's rotation speed, essentially, you see that it's the background of the spectrum becomes less when you go to higher rotational speeds. So
yeah,
say something like that.
let me am I sharing again?
Yeah.
Yeah.
So yeah, it basically has to do with the tidal spectrum, and you do not see exactly the tidal spectrum for the parameters that we chose, but you see if you allow for the hemispherical ocean. So as I said again, so I'm not okay. Yeah, so in the first phase we have a hemispherical ocean, as you know, and in the earliest eons we have the global ocean. And so for the hemispherical ocean, the imposed effect of continentality and the imposed effect of the coastlines would distort the spectrum of the torque, allowing for these minor resonances. So if you look here, the difference in the global ocean scenario, you have these resonances which are uniform and which are of a typical amplitude that varies regularly as you go backwards in time. But when you allow for the hemispherical continent, you distort the spectrum into minor resonances. So for you allow for smaller amplitude resonances. And this is an effect of the imposed coastlines and the imposed continentality effect. So that's why we have this major resonance, because it's associated with the response of the global ocean. It's typically how the global ocean would respond in its normal modes of excitation to the tidal forcing. So this is the coupling or the overlap in frequency between oscillations that are happening in the oceans and the tidal forcing. But it is different when it becomes a hemispherical ocean, because this coupling or this overlaps would generate different kinds of resonances of smaller amplitudes, as we see here. We also have major resonances. So you see this one is major, for example. And here we have major resonances, but
yeah,
are also minor.
maybe Mohammad, it's good to tell that in this plot we are nearly in the plot you were mentioning, the 10⁻⁵,
Yeah.
and we are just moving from about 1 to about 2.
Yeah.
Okay.
You see?
Yeah.
Okay.
Yeah, so basically, if you look at the spectrum, so this is not exactly the value that we fitted, but it's very close to it. So we start here around 1. So you capture 2 of these resonances, minor resonances here, and then you go into a smooth spectrum, and then you transition into the global ocean with its major resonance.
Yeah.
So this is what happened exactly.
Okay. Another one. So to clarify, so for the last 1 billion year, you determine the position of the hemispherical cap based on well, geological reconstructions, plate tectonic reconstructions. But what about the period before that, when you have the hemispherical?
Yeah, so good.
Oceans.
I forgot to mention that.
Move the position of that one, and what's
yeah, so I forgot to mention that, because basically we do not have a continuous model beyond that. So the model that we got from the literature of the recent one of Meredith et al. Is only over the last billion years. So what we had to do was to fix the hemispherical continental cap to the last position it had at 1 billion years. So we fixed that. But but in hindsight, it really doesn't matter, because we move at this time into the smooth variation. So we avoid the resonances and we move into the background of the spectrum.
Okay.
We have captured the resonances with this evolving hemispherical continental cap, but we beyond 1 billion years, we move into the background of the spectrum. So we're not missing out on any resonances that can occur because of the varying hemispherical continent. But yeah, because we lack a continuous model of plate tectonics beyond 1 billion years, we just fixed the position of the cap to the last position it had at 1 billion years.
Okay, so is that different from Webb?
So what Webb does is different, because what Webb does was that he took a hemispherical continent and he computed the response of that continent at different configurations, so at different positions on the sphere, and then he took an average. So he took an average response of an average hemispherical continent, just capturing the average response of this continent. Yeah.
Okay.
The web does not allow for the evolution to physically follow a plate tectonic model.
Yeah.
And maybe one thing can be added by, can you go back to the plot of the Earth-Moon distance evolution? Yes, yes, stop. And just to mention that the red dotted line is Webb's model, but it's not really Webb's model because it's beyond what Webb did, because Webb, it's a model of Webb, but this is with the search of the best parameter that would fit the age of the moon and the present tidal dissipation. Because our question was, of course, in the paper of Webb, he took some value, and with this value, he missed the age of the moon. And I think it did not fit either to the present tidal dissipation. But we thought, okay, let us really be fair, and let us try to see if with this model, we could fit both, for some other parameter value, fit both the present tidal dissipation and the age of the moon. So we search, Mohammad searched for all the parameters, and actually you find a solution that fits well to the present age of the moon and to the age of the moon and the present tidal dissipation. So this is the plot that is given in this red dotted line, but this is already some new result which has never been published. And the surprise was to see there are two things. It fits a little bit less. The fit with our model is a little bit better, but it would not be significant, I would say. But what is impressive is the difference of fit with the geological data. And it's the same thing for the oceanic model, the yellow one. This global oceanic model, we thought, so whether it would be possible to fit both, because that was the only constraint we give, the present tidal dissipation and the age of the moon. So the question was whether with this model, much simplified, it was also possible to make this fit. And actually it is. And the fit is quite fair. But it again, it doesn't fit to the geological data. Okay, now we have Linda.
Mohammad, thank you so much for a fantastic talk. It was just wonderful. I learned so much from this that I didn't understand before. Thank you. And I have two comments. One is that the combined model seems to conform with the paleo data in that around 250 million years ago, you have a flat, you have no change in Earth-Moon distance. And so right now there seems to be paleo data that indicates actually a decreasing distance over, a certain period of time of several 100 billion years ago that was discussed back in after the talk that I gave. But if that can be filled in with more data, maybe we will see sort of a flattening of the change, so no change. So that is very exciting to me. And yes.
Can I share the screen? Maybe I can share my my screen to go to the AstroGeo. I will share it here.
So this was data that was compiled by Zhang et al.
Yeah, but I just want, because to illustrate, because we are speaking here of this.
That's correct. Yes.
Of this plot here. Yeah. So here I am. Yeah.
Well, it's a little bit offset from what I was thinking, but.
So you see, this is the question is. This is the one you.
Yes, but the data show that the flat area should be centered on 250 million years. So I wonder if there's some way.
So yes, so it is very exciting to get new data points here.
Yeah.
to
That's
see
right.
if this occurs, because this here is the existence of the first resonance, and this is the second resonance. And it is very, so this is really some goal for cyclostratigraphy, because of course there are some points, but some of them with some discussion, I heard that this has to be revised somewhere.
Okay,
and,
absolutely, yes. I have another comment, if you can keep that plot there. So I agree that a renewed campaign to look at Phanerozoic data and sort of reanalyze what's there and start to bring in more data. And I think that this is being done. I have another question that's maybe related to that. And what would be the effect of adding the effect of the growth of the inner core? Would that shift everything? I mean, the growth of the inner core presumably would impose a reverse direction, because of the change in the moment of inertia.
Yeah, I understand. So first off, I did not explore that effect quantitatively, and I think the variation in the oceanic spectrum is much more dominant than that. The question becomes whether it's necessary to go for such a variation to explain any kind of variation that we see in the data or not, or it's sufficient just to stick to first principles of oceanic dynamics, solid dynamics, maybe atmospheric dynamics, or we have to go into some scenarios of growth of core, because if I remember well, the effect is not that significant.
Well, there was one estimate done by Runcorn back in the 1960s, and he was showing that the effect was at least several hours a day with the sudden growth of the inner core. It went from like 24 to 27 something hours per day difference. So I will share that old paper with you.
Yeah, so I'm not very familiar with the literature on this problem. But, yeah.
Okay. All right. Thank you so much. I actually have to
just to make a comment on that.
Yeah.
Because of the time problem, because of this, it's like many places in science, then there were plenty of scenarios that try to find some physical way to explain this problem by adding some effects, like, for example, atmospheric tides or things like that. So the question, I think, now will be very different, because we have some sounded physical model that explain things. So, of course, there can be some additional physical effect, but they are no longer necessary in some sense. They can be here, but it changes a little bit the way you can think of the problem.
Absolutely.
And, I think there will be a large revision of many things. Of course, we will look to this. Okay.
Thank you so much. I must actually go. So thank you. Thank you again. Bye-bye.
Okay. Bye, Linda.
Bye.
June?
Yeah. Thank you very much for a very clear talk. I really enjoyed. So, Mike, I have a couple of questions. So first question is, in your model, ocean volume is held constant? Yeah, because it's a little, because like geological, these days, we talk about we have more voluminous ocean in the past. So can you comment on if you, for example, change the ocean volume over time? You have a more large ocean, let's say, my estimate is like a 2.5, you have 50% more voluminous ocean, and the 4GA, you have like a double the ocean mass. So if you have that kind of stuff in your model, what kind of influence you have for your results?
Yeah, let me just share again one thing. Yeah, so I'm aware of the growing understanding of changing volume. It's definitely not conserved. Let me just share to talk about the effect of that. So basically, the effect of oceanic volume would be captured into our oceanic thickness parameter, right?
Right.
Yeah, so the signature, so I'm not showing here the signature of oceanic thickness, but I can describe it properly. Yeah, So here I'm showing the variation of the torque as a function of the dissipation time scale. It's a fixed thickness. But the effect of varying thickness is in fact very similar to the effect that you see here for the solid contribution. So basically, varying the oceanic thickness on the spectrum does not completely distort the spectrum. So you would still have this scaling, this background which scales with the same behavior as a function of sigma, and you would still have these resonances with the same kind of behavior in both the hemispherical and the global ocean. The difference that would be is that the spectral position of the resonances would slightly shift, very similar to what you see here. If you can notice the difference here between the blue and the red curve, you have a slight difference in the spectral position of the resonance and a slight attenuation in the resonance amplitude. And this is exactly the effect also of the oceanic thickness. So the oceanic thickness variation would slightly shift the position of the resonance, and it would slightly attenuate the amplitude. So if we want to allow, I mean, I did not yet allow for varying oceanic volume, but if we want to allow for oceanic volume variation, the existence of the resonance is a robust feature of the model. So you would still have the resonances there with their consequent variation of the Earth-Moon distance. You might have a slight variation in their position and a slight variation plus or minus in their amplitude. So
okay, thank you.
Yeah.
Okay, great. My second question is actually probably more for the audience. So yeah, actually this slide is good one to see. So because of my lack of I don't have like a thorough understanding of literature, you have like a 3.2 GA point for like a tidal rhythmite, and how like expert in this field, how this data point is regarded, because I don't see this stuff very often in other papers. So do anyone other people have some comment?
You mean the point at 3.2 billion year?
Yeah, that's right. Yeah.
Group, yeah.
I must say that the point we have been already looking more deeply to this data point here, as it is published in this paper that we put here. We already put in our paper that this has not to be taken too seriously because it's not clear how it was derived, but there is presently quite a large effort to reanalyze this geological location. And so we can expect some, the location is here, then there is some, it's a Moody group, it's in Australia and South Africa, yes, sorry. And yes, there is a big effort to reanalyze this data and our location nearby. So we can expect to have, and there is already one paper that is online, that is in archive, which has a different interpretation from this point. So, which is not totally contradictory with our curve, but which will put the value much below here in the in this graph.
Okay.
Yeah,
okay. Thank you. Yeah. Thank you. Yeah. Thank you very much. Great.
Maybe Margaret can comment better on that.
Well, I mean, it's totally unclear. So the point that is shown here, it's just from a review paper, and then they just give an age of the Earth-Moon distance, and they say that it was calculated by in a previous study by Erickson and Simpson 2000, but they
didn't give anything.
They didn't calculate that, and also from my understanding, that Earth-Moon distance doesn't make sense if you look at the interpretation of a number of tidal laminae that they counted. So, yeah.
So globally, we found that the cyclostratigraphic points can be more trusted than the tidal rhythmites. So the blue points here.
Okay, thank you. Thank you very much.
And let me remind you that, in fact, June will make the next AstroGeo Seminar And he will address specifically the early part of the Earth-Moon evolution and probably the growth of the ocean and all that. So let us continue with Alberto.
Yes, thank you. I have there was a great talk, Mohammad. I really enjoyed it first. I had a question about that always bothered me a bit about all of these hemispherical ocean thing, and actually has to do with the hemispherical continental cap, in the sense that if we look at the Earth today, the total area of the continents is quite a bit less than a half, right, of the total, and it was even less in the geologic past. However, we look back in the past and exactly how the continental masses have grown. They have grown. They haven't decreased, right? So they were. So what happens if, for example, you change the area of the cap, right, to be less than 1/2 of the area? I'm just curious, you know, maybe you've done some sensitivity analysis of what that does, right?
Yeah, so I would ask you to wait a little bit because we have a forthcoming work on that.
Oh, okay. No, that's fine then. No.
Just to tell you, Alberto, you see, physicists are, it's like in the joke, you see, where...
yeah, there's a spherical cow, yes.
Yeah, spherical cow or spherical horse to win the race, the horse race. So we have, in order to make analytical, when you make numerical computation, you can take any shape of the continent you want.
Yes.
But it's very cumbersome, and you lose the physical insight. When you make some analytical computation, like here, you get much more physical insight, but the computation is very complex. So you need to make some simplification. And you expect that by this simplification, you will still have the skeleton of the story. And this is what we have been doing. And so the most obvious thing is the global ocean. This is the most easy way to handle. Then there is this hemispherical cap, which is something, because it gets quite complicated when you make it at any orientation, which is what Mohammad did. But when you want to make a smaller cap, it's a huge work additional.
I see.
So we have undertaken this work, in particular Pierre, who left, but Pierre Auclair des Retours. So this work is currently ongoing, but it's not a simple parameter that you change in the code to go from an hemisphere to a cap of a various size. It's a huge work.
Yeah.
So as Mohammad say, stay tuned. We may give you the answer because, of course, we wonder about this question. But the general idea is that you see in the spectrum, what happened, you have a big change when you go from global ocean to hemispherical continent, because you break the symmetry of the problem. And then you have all these peaks that appear, additional peaks that appear in the spectrum. Of course, we expect that there will be some slight change by making some more realistic configuration, but we don't expect huge variation in the general physics. That's the idea.
Okay, I appreciate that. Thank you.
Are there additional question or comment? Okay. So if not, I thank everybody for attending this talk, and we will meet again in the end of February. Let me check the date. It's on the 23rd, June Korenaga, who will speak of the very early stage of the Earth-Moon system. And that will be very complementary to the present talk. And I hope it will raise the question of the growth of the ocean and how to improve the model. Okay, so goodbye to everybody and meet you in February.